for the sense of belonging. Some people die before they fulfill their desires. Such a waste of existence. Spend our life searching for the sense of belonging. Some people die before they fulfill their desires. Such a waste of existence.
Anxious earth is rising. Anxious earth is rising. I'm so happy.
We spend our life searching for the sense of belonging. Some people die before they fulfill their desires. Such a waste of existence.
I don't hear anything. Okay. Hey, this is Double Triple Channel. How is everybody? How are you? Hello. This is the Double Triple Channel. My name is Ron. It's February 1st, 2025. If you can believe that, 2025. I'm in rural New Hampshire. I'm surrounded by forests and wild animals and all kinds of stuff. It's pretty cool. I like to talk about science and science fiction and film and civics and old movies. I'm vegan, so talk about veganism sometimes. I neuro-D. I got social dyslexia, so you might hear that every once in a while, and language dyslexia also. So I do a lot of different stuff tonight. Today I titled the stream, what did I title it? Geek Talk and Reading YouTube Comments. Didn't do a lot of planning as usual, because I wasn't expecting to stream today, but we got up to lots of sun. The temperature is actually dropping outside. It's been dropping all day, all night actually. Or, well, yeah, since about 4 in the morning it started dropping. And it's supposed to get down to minus 12 tonight. And I don't know what it's going to be with it. That's minus 12 Fahrenheit, so that's minus 25 or something, minus 20. Yeah, 25. Something like that. Cold. It's going to be cold. Yeah, over minus 25, minus 30 maybe, huh? Celsius. So what I decided to do was go ahead and stream because I got lots of sun, and I opened up the windows here, and it's heating up my room. Normally I gotta retreat to the warm room when it gets cold, but this room out here is warm up. We're 13.5 degrees, so that's enough for me to do a stream until it starts getting cold again. So that's what I'm doing, and I wanted to. So I didn't do a lot of planning on it. That's what I'm trying to get. That's the point I'm trying to get across here. I didn't do a lot of planning. Didn't plan the stream as usual, but I want to get out here and do a stream since it's going to get really cold, and I don't know how long it's going to be cold, and blah blah blah. So I don't know when I'll be able to stream again. So I wanted to get out here and do this stream, and I've been watching YouTube videos of science streamers and stuff like that. Science YouTubes and stuff like that. So that's kind of where my mind was at, but we'll just go from there, I guess. There were a couple of interesting things that I was doing. The one thing that I've been interested in talking about for a long time is time. What is time, right? It seems like it's something that's very simple. Everybody knows what time is, right? It's what the clock says, right, or whatever. Throughout all history, people thought time was just a steady thing. It was the same all the time. No matter where you were, what you were doing, whatever, time progressed at a set pace all the time. And they understood that maybe if you were your mind was in a different state, it might seem like time is going faster or slower to you psychologically, but as an objective measure, time was going at the same pace all the time. And then Einstein came around and blew that out of the water with the theory of special relativity. And we discovered that, and general relativity, and we discovered that time doesn't always go at a steady pace like that all the time. If you're moving really fast, time will slow down for you relative to people who are in an outside reference frame. If you're in a gravitational field, then your time will slow down relative to somebody who's not in that gravitational field, and so on. So. But the whole thing is, what is time? I mean, what the heck is it? It's a physical. Some people say, well, it's just our own. As humans, we see time as it's a psychological thing. We just make it up. It's not real, and it's just an illusion that our brain makes up or whatever. And I don't think that's true. I think their time is a real thing. I think there's an objective thing out there called time. And with the current theories of relativity, they put time and space as kind of a they call it a continuum. It's just when you're moving fast in one, then the other will slow down. If you're moving fast in space, then time will slow down. If you're not moving fast in space, then time will go faster. That sort of thing. So they put it all into one thing called space-time. And it's 3 dimensions of space and 1 dimension of time. But the thing is, what is time? What is it? We still don't know what it is, what causes it. Stephen Wolfram has a stream he does, or stream he does on Twitch and YouTube, and I asked him about it, and he didn't answer me the stream that I asked him, but a subsequent stream he went and did a whole, like, half the stream on explaining what time was from his perspective. And his whole deal is that the universe is made up of calculations and such. I'm going to check my sync here really quick just to make sure. Okay, so it looks like my video is lagging a little bit here. All right, so sorry about that. I'm going to fix this really quick here. All right, let's see if that's better. No. All right, we'll figure it out here. Hey, that's much better. Okay, I think we can go with that. What do you think, huh? All right, yeah, I'm going to go with that. All right, so I asked Steve Wolfram to get his opinion. I was asking a lot of different people, you know, people who do stuff online, and his whole idea is he wants to change the whole paradigm of science to be computationally based rather than you know, theories based on equations and math and stuff like that. He wants to make it computational. So his idea was that time was what it takes to do the computation. You know, the universe does computations to make things happen, and his idea is that what it takes to do the computation. And when you're moving through space, then there's more computation being done, so time slows down. I think that's a summary of what he was saying. Don't quote me exactly, but that was his idea. And you know, one of the main things about time is there a direction to time? You know, why? You know, why does time? I mean, it does have a direction as far as we know, right? You can only go one way in time. You can't go back to the past. You got to keep going forward all the time. But in space, you can go forward or backward or up or down or whatever. So that's kind of weird, isn't it? But all the math, all the theories and everything say that time can go backwards. So maybe this arrow of time is something that's emergent on only the macro level. And one of the, you know, the most popular or the contending theory as to why time is a vector, you know, in one direction, is that entropy. It's because of entropy. And we'll maybe I'll talk about that in a little bit. But I'd like to see if I can find this video that I saw earlier, and just play it for you. It's a YouTube video. All right, let's see here. I think I found it. All right, it brought me to one of this. All right, this could take me a second to find this video here, but it's an interesting video. This guy talks about time. What the heck? Oh, YouTube put a they've got a damn ad covering up the content on their site, and there's no way to get rid of it. What? All right, let's see here. I don't remember. It was a couple years ago. Let me do a search for this here. Search for time. Yeah, the name of this guy is Dr. Paul M. Sutter. And he calls his channel Ask a Spaceman. So, all right, let's see if I can find it here. Time crystals. Oh, that's kind of interesting. That's something we could talk about at some point too, maybe. I don't know enough about it to talk about it off the top of my head, though. let's see. Time travel. Okay. Oh, he's got one here about entropy. You could watch that. Why is time so hard to understand? Okay, I think that was the one I saw. Right, that one's paused. Okay. Now I got to see if I can get this window up on my video, on my thing here. All right, let's see. Oh, I think we can do it here. There we go. Okay. All right, I think we got it here. Sorry about this. This is kind of whack, I know, for the thing. All right, let's see what this looks like here. Yeah, that's covering most of it there. Okay. Now we got to make sure we got audio. Yep. Okay, it looks like it's there. Okay, monitor and okay, we're going to monitor it. All right, let me play a little bit of this.
It's all meant that time is weird. Time is weird. Like, it's so hard to describe just how weird time is. And the weirdest thing about time.
Okay, so, all right, we'll watch this video. Let me show you here. This guy is, before I do it, very cool. Paul has put his stuff out for Creative Commons so we can reuse it, which is very cool. Thank you, Paul, for doing that. We really appreciate that. So now let's watch his video, and then we'll talk about it a little bit. And he's got another one too on entropy. We'll watch that too, about time and entropy. All right, so we'll watch this. When the ads come up, I don't know, I'll just try to blank the sound or something. I don't know what to do.
Let's just all admit that time is weird. Time is weird. Like, it's so hard to describe just how weird time is. And the weirdest thing about time is that it has an arrow. It has a direction. It has a flow to it that space doesn't, right? I can go left or I can go right. Super easy. I can pick either one. Doesn't matter. I can go forward. Or I can go backward. Again, super easy. Doesn't matter. I can go up. I can go down. Up is a little bit challenging, but that's because of gravity. But like that, but out in space, it doesn't matter. I can pick any direction I want. But I can't pick which direction I want to go in time. I must go forward in time. We all must go forward in time. It looks like time travel into the past is forbidden in our universe. And I have other videos explaining some examples and how they're forbidden. We don't fully understand why time travel into the past is forbidden. But even without that, it's just like time goes forward all the time. I don't know how many time puns I'm going to accidentally make in this episode. It's probably going to be a lot. But just time goes forward. Time must go forward. And this is a property of the universe that demands explanation. We can't just let that go. We can't just wave that away and say, yeah, when the time goes forward, who cares? No, this is a property of the universe that we must explain. Now, it could be just like a trick of the consciousness, like some game our brains are playing in our heads and time doesn't really act this way. That doesn't seem right for various reasons that I'm not going to get into because I'm going to paint a physics picture of time. So I'm going to assume that time is real, that time does go forward. This arrow of time is not an illusion. It's a real physical thing. That's the game I'm playing. And in this scenario, in this picture, in this worldview, the arrow of time must be explained. So here we are. Time has an arrow. Why? Why does time have an arrow? And what we do as physicists is look around. Are there any physical laws, any theories, any models, any equations that have themselves a flow of time baked into them, where we can point to and say, okay, guys, I figured it out. The reason time has an arrow is right here, equation 13.4. In this derivation, time appears and time has an arrow and it has a direction. This physical process has a direction, a sense to time that's already baked in, and hence the arrow of time flows through that. Now, time, the variable time, the concept of time appears all over in physics, like everywhere, but it's just a parameter. It's just a parameter that tells you how a particular system evolves. You can tune it, you can change its value. And so the equations, even though many equations in physics have time inside of them, time appears in the equation, there's no particular arrow to that time. Almost every single physical law that we have, time can run forwards and backwards just as easily. There is no arrow. Time appears, but if you look at, say, how particles interact and the forces that govern how they interact, they can go forwards and backwards as easily as they please. If you look at how gravity, how objects behave inside of gravitational fields, they can go forwards and backwards as they please. So the fundamental rules that govern our universe don't care about time, are fully reversible. And yet, that totally contradicts what we see in the world. Most everything we do is not reversible, is irreversible. There is an arrow, there is a flow. You can immediately tell. If, say, this video were playing backwards. You would just know. If you were to look at some process, a video of some process, or an interaction or a scenario at a macroscopic level, you would immediately know. You have an intuition. Say, yep, that one's backwards, forwards. That one's forwards, backwards. Like you just boom, 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 boom. You wouldn't even think about it. The macroscopic world has an arrow, has a direction in time, but the microscopic world pretty much doesn't. There is this very obscure interaction involving the weak nuclear force that does have an asymmetry in time, but I'm not going to talk about that here except to say we don't think it's very important because that interaction basically is very, very rare. And so it doesn't seem to be fundamental to the universe. Happy to talk about that in another video. And instead I want to focus on something else. There has to be something in physics that takes us from the microscopic world, which can go back and forth in time as easily as it pleases, to the macroscopic world that doesn't, that is locked, that has a flow, that has an arrow. There has to be a bridge between those two worlds. And there is a branch of physics that provides a bridge, and that is the branch called thermodynamics. Thermodynamics. The description, and who would have guessed? Who would have guessed that this would be the one, that this would be our best guess of explaining the arrow of time? Things like temperature, and pressure, and volume, and entropy. All this, Carnot cycles, and pistons, and cylinders, and in particles inside of boxes. Like, raw thermodynamics is actually a way of connecting microscopic behaviors to macroscopic observables.
For anyone struggling with dementia, do not drink cold water.
And this is done through the to macroscopic observables. And this is done through the language of something we call statistical mechanics. When we say, like, okay, we have a bunch of particles inside of a box, like we fill up a bottle with some gas, let's say, for example, and that gas has a temperature and a pressure. Is there something we can measure? Stick a thermometer, pressure scale, whatever, you can measure that. These are macroscopic observables, things you can do on a lab bench that connect to microscopic processes, to the individual motions of particles that we can't see. The countless numbers of particles inside that volume, inside that gas, inside that cylinder, inside that bottle. If the temperature is higher, that means the particles are jiggling around faster at a microscopic level. And if the temperature is lower, they're going slower. The pressure is just these particles hitting the wall, constantly hitting the wall. If there's higher pressure, they're hitting the wall more often, or there's more of them to hit the wall. If the pressure is lower, it's not so much. So you have a macroscopic observable that connects to microscopic behaviors, and the technology of thermodynamics and statistical mechanics are what make that possible. So we have the mathematical descriptions of the microscopic stuff, of the individual motions of particles, and we have the mathematical description of the macroscopic behavior of the ideal gas law and pressure and all that juicy stuff that we all learned in high school. So that's potentially interesting. Here is an apparatus that connects the microscopic to macroscopic world, and the problem of time appears to demand some sort of connection between microscopic processes and macroscopic processes, and this is why we think entropy has something to do with time. Entropy is a measure of disorder in a system. I'm going to do a whole other video just on entropy. For now, we're just going to use that definition. The second law of thermodynamics says that in closed systems, entropy must go up. Entropy itself is a macroscopic observable measurement for something happening microscopically. Entropy goes up. Entropy must go up. Systems must move from disordered to disordered. They must become more chaotic with time. Systems must move into their future. Systems cannot travel into their past, they must travel into their future. Systems go forward in time. Systems become more chaotic. Is this it? Is that the connection? Is the reason we have an arrow of time because systems must go from ordered to disordered, must become more chaotic? Maybe. That's our best guess. Thanks so much for watching. I hope you enjoyed. Like I said, in my next video, I'm going to dig deeper into this concept of entropy. But if you like this, don't forget to like and subscribe, share, make sure notifications are turned on. Go to patreon.com/pmsutter to help me help you understand entropy and maybe time. I'll see you next time.
All right. So that was his kind of giving an overview of the whole thing. What all the problems. Physicists don't know what time is. I don't think I heard him mention that. What physicists do is they say, just in order to do their job, they got to say what time is somehow. They say time is what the clock says, or what a clock says, and basically they just compare two things. If there's an event that happens on a regular basis, then they call that a clock, and they say time is what the clock says. So in other words, they don't answer the question. And so that was a good overview that he gave there anyway in that video, where he talks about what the different stuff is. Oh, I forgot to check my audio here, make sure I'm in sync again. Yeah. Okay. So there was one thing that he said at the very beginning of the video, though, that I thought was kind of interesting. And I can talk about it a little bit. Is he was explaining in space you can go forward and backward, right and left, up and down, but in time you can only go forward. You can't go backward. Into the past. But when he said up and down, he mentioned something there. He said going up is a little difficult because of gravity, and going down. And what's interesting about that is that with time, that happens too. When you get to the event horizon of a black hole, you're stopping time from going forward, right? When you get to the event horizon, time virtually stops, right? It approaches zero. And there are some theories that say when you get past the event horizon and go into the black hole, that time goes the other way, that you go into the past. The time goes backwards into the past. So I thought it was very interesting that he mentioned that. And it just kind of made me think, that time does kind of act like space in that regard when it's around gravity. If you're in a very in a black hole, very the highest gravity, according to some theories, it does. You can go backwards. You can go up and down or whatever. And so some theories say that space. They use the word time-like and space-like, and they say that time becomes more space-like and space becomes more time-like. And what they're saying is that when you get to the event horizon, you can only go one direction in space. Right? You're at the event horizon. You can't go out from the black hole anymore, right? Should I bring up my little? I'll skip. I don't want to get. You know what I'm talking about, right? You get to the event horizon of a black hole, and the gravity is so strong that light can't even escape. So space is acting like a vector, right? That can only go one direction, down into the black hole. But the whole problem with all of these theories about the black hole is that once you get to the event horizon, everything stops. Nobody moves, right? From the perspective of an outside observer, and from the perspective of an observer in the black hole or at the event horizon, their time slows down so much that the life of the entire universe passes by them before they do even move a little bit, because their time is going so slow. So a lot of stuff about time that's just so bizarre. But anyway, that was a good introduction to it, and he talked a little bit about entropy. He's got another video about entropy that I want to watch, and we'll play that too. And then we can talk about entropy a little bit more. That one, I think I need my little sketch pad here to talk about that a little bit. But yeah, entropy is kind of a weird thing. The way that I think about entropy is that some people use the word order and disorder, and that's not a really a good way to do it, to talk about entropy. Entropy, to me, a good way to understand it is that higher entropy means more clumpy. Things are more clumpy. And lower entropy means things are more homogeneous, spread out, or even. I think that's a good way to think about entropy. But it does give a direction to time on the macroscopic level. On the microscopic level, don't think so, because stuff forms into quantum particles, and you don't have that entropy effect like you do at the macroscopic level, and it's actually a probabilistic type of thing. And I think he mentioned that a little bit. It's the probability that if everything's clumped together or almost clumped together in high entropy, then the likelihood that one particular thing is going to move and be even closer to the other things is lower because there are fewer places for it to go than the likelihood that those particles will move out into the space where there aren't other particles. So, and things progress to the more probable, right? Everything's like that, right? The most probable thing to happen will happen. And so that's what happens in entropy. That little clump of whatever you've got, could be particles, could be energy, could be anything, will spread out into the areas where there isn't that thing. That they think that is what gives time an arrow, because that is kind of a one-directional thing, right? Entropy wants to go to less entropy. More entropy wants to be less entropy. Things want to spread out, but they don't want to clump back up again. In nature, usually. There actually is, you can figure out the probability. Somebody did this, they figured out the probability, like in an average room or whatever, and you have all these oxygen molecules in your room, and they thought, okay, well, there is a probability, a very small probability, that all these oxygen molecules could just, by chance, bump into each other and slowly propagate into one corner of the room, and everybody in the room would suffocate. But the probability is less than, once in the life of the universe or something like that. It's so improbable because there's so many molecules and so many of them to do that. And that would be right. That would be reverse. That would almost be like a reversal of time. If you imagine taking a room and putting a clump of oxygen in the corner of the room, it's gonna spread out throughout the room, be kind of evenly spread out after a while, right? Going forward in time. But if you think of all those, oxygen molecules bumping into each other and randomly just going into the corner, then that would almost be like going backwards in the way that time progresses. Anyway, so that's the big leading candidate as to why time has an arrow, but it doesn't explain why there would be time in say in the quantum realm where you don't have these particles moving around and entropy like you do have in the macro world. So it's an interesting question. It's an interesting problem in physics. What is time? What is it? So let's watch his other video. He's got he put it up right up here because I guess people like to watch this one. So the algorithm wants to put this up here right here. So I'll do that one too. And let's see here. All right, there we go. All right, we'll run that one.
Big Pharma tried to silence me when I said lemon contains a nutrient that naturally controls blood sugar.
All right, there we go. And this one here too, he says, right? He says it's this was back in 2018, so this was just seven years ago. And yeah, he released this one into Creative Commons too, so we can watch this. Cool. All right, so we'll watch this, and this one he's talking about entropy and time or whatever. All right, here we go.
All right, entropy. The big E. One of the most frightening words in physics. I mean, if you want to turn people off at a party, start talking about entropy. This is probably why I don't get invited to a lot of parties. Now, entropy. Entropy is a concept that was developed in the mid-1800s to describe the amount of disorder in a system. I know that's a very, very loose definition. There's an actual mathematical definition. We're going to dig into that in a little bit in today's video. But entropy itself, I just want you to think of, is a measure, a way of keeping track of the amount of disorder in a system. And the second law of thermodynamics says that entropy must go up. If you have a closed system, it's cut off, it's not receiving any energy, then entropy must go up. The system must move from disorder to disorder. And we think this is maybe somehow linked to the arrow of time. The reason there's a past is different from the future is because systems must move from disorder to order. I keep flipping those around. Why do I do this? Systems must go from order to disorder. Systems go from the past into the future. So, okay, but why? Why must systems go from order to disorder? They didn't have to, but why? Like, if the second law demands this, why is the second law of thermodynamics true? And I'm going to give you an example. Entropy is a way of measuring disorder. It's a way of counting. It's a way of counting. If I have a box full of particles, a gas, whatever, I just have some system that I'm looking at, and there's some temperature associated with that system. I stick my thermometer in, my probe thermometer, okay, it's 150 degrees Fahrenheit. Okay, great. What does that mean? It means that the gas particles inside that box have a certain average velocity. They're all wiggling and jiggling all over the place. Let's say I were to freeze frame that just for a moment. Just take a snapshot. And I captured all these particles in mid-motion. What if I were to take two of these particles and just swap them? When no one was looking, I just swapped them around. You wouldn't notice, right? You wouldn't know because these particles are identical. You can't tell if this is that particle A and particle B, is this particle B and that's particle A. You can't tell. So you can swap them around with no change. And in fact, you can move them around a little bit. You can pick up this one and tweak it, just bring it up over here, just a little bit. And the temperature wouldn't change. You can rearrange the system. And I'm moving my hands all like Kung Fu style for some reason. You can rearrange the system without affecting the temperature or any other thing that you would measure, the pressure or anything like that. The number of ways you can rearrange the system without affecting things like temperature and pressure is the entropy. That is the definition of the entropy. If I can keep this temperature but start rearranging it, it's like, okay, here's one way, 2 ways, 3 ways, 4 ways, 5 ways, 6 ways, 7 ways. And you keep track and you add up all those different ways, that is the entropy. Now, why must entropy go up? Why must disorder go up? Because there are so many more ways for a disordered state to exist than an ordered state, while maintaining the same pressure and all the other thermodynamic measurements and observables. I like using the example of a room. Let's say you clean your room. Place for everything in its place. It's spotless, totally organized. Ideal, platonic ideal of a room. All right? It's all set. How many ways can that room be clean? 1. There's only one way for that room to be clean. How many ways are there for the room to be messy?
Carrying around extra fat is dangerous. This is how you get rid of it.
If you want to drop this, start eating more.
How many ways are there for the room to be messy? Like countless ways. Countless ways. You leave a sock out, there's one way. You have a pen over there, there's another way. There's a little smudge of dirt, there's another way. Like 2 socks out, you have 3 socks out. You just count up all the possible ways to have a messy room. It's overwhelming. It's some gigantic number. There's so many ways to have a messy room. There's only one way to have a clean room. Only one way to have an organized room. So let's imagine if a tornado happened inside of your room and totally reorganized everything. If you opened up that door after the tornado hit your room, would you expect to see a messy room or a clean room? A dirty room or an organized room? which would you expect to see? You would expect to see a messy room. You'd expect to see a disorganized room, because there's only one way for it to be clean, but many, 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 many ways for it to be disorganized, many ways for it to be chaotic, many ways for it to be disordered. Even though it's not impossible, that tornado could have came in, rearranged everything, and put everything in just the right spot. Man, 1 in a quadrillion chance of encountering a perfectly clean and organized room. But the statistics are not in your favor. The statistics aren't there. There's so many more ways to have disorder than order. So systems like a gas in a bottle, or the air in this room, or a ball rolling down a hill, or anything that depend on so many countless tiny little interactions between the microscopic bits, the number of ways it can be in a disordered state are always going to be so much greater. Like ridiculously greater. Like so much so you can hardly even write this down, than an ordered state. And that's why entropy always goes up, because if you have a system and it's doing its little microscopic system things, if you started in an ordered state, there are just so many more opportunities to be disordered. So many more random arrangements of particles that can be disordered rather than ordered. So the entropy must go up. It must. So, is that it? Is that why there is a flow of time? Because entropy must go up, because there's so many more ways for states to be chaotic and disordered than ordered? Maybe. Like I said before, this is our best guess. It's our best guess, but it leads to a very tricky question. If you're going to say that this is the arrow of time because entropy, because of the statistical thing, okay, why was our universe 13.8 billion years ago, in the early days of the Big Bang, why did it start with such low entropy? Why did it start in a state that let us slowly get disordered in such a way that we could have stars, multiple generations, planets, life? How do we start in that, what appears to be a very special state? Got nothing. Well, I mean, there are some ideas out there, but that's another video. I'll see you next time. Hope you enjoyed this. Go to patreon.com/PMSutter to help support this show and all my education and outreach. And you can also like, share, and subscribe, all that good stuff. Check out another video. Have some fun on the channel. Feel free to ask me questions below, and I'll see you next time. Now clean your room.
In honor of
All right, so I think we got audio now. So he explained there, like what I was trying to explain, but he did a lot better job at it. Explained why why entropy is one of the candidates for why they think time might have a direction like that. It's just probability, you know. But I don't think he mentioned anything about quantum stuff. He was kind of giving a general answer there, so that's kind of an issue. You know, what happens at the quantum level with time? You know, it's a question. What do you do? You know. So it's kind of hard to use that as the. Yeah, now it could be that time doesn't have an arrow or doesn't have a vector. It can go forward and backward. But the reason why we only see it going forward is because we live in the macro world, and we can only see, you know, we can only see stuff happening in one direction. That might be what's going on. And in extraordinary cases, like in a black hole, or you know, with particles and things like that, maybe. You know, there's a particle called a tachyon, which scientists have proposed as a particle that is like a photon, but it goes at the speed of light backward in time. I think that's true. Let me look that up here before I go. Or maybe that one's faster than light. Look this up here. Make sure I got this right here. Oh no, that's a faster than light particle. Okay, that's different. Well, what's the name of the particle that goes backward in time? Oh, I know what it was. It's any particles. Right. Antimatter. You know, each matter particle has an anti-particle that has the opposite charge, and they say that it might go backward in time. That's a proposed theory, that any particles go backwards in time. That's what I was thinking of. So it might be possible that at the quantum, in the quantum world, that things can go backwards in time. And there's also a theory about, this is kind of getting into the weeds a little bit, but when photons, there are no particles, right? Everything's a wave, right? They call them particles, but they aren't actual point. They're not points. They're not even clumps. They're waves, right? A photon, a single photon goes out as a wave front, and it travels across, right, as a wave front, just like a wave on an ocean, except it's through space and it's a little bit, there's more involved in it, but that's what it is. And then when it hits something finally, then it will collapse down to one electron or whatever particle that it interacts with. Before we go any further here, we got some chatters here. Let's see. Oh, Erum. Oh my God, I got a raid, Erum. I'm not going to tell anybody, but while I was playing that video, I was going and playing trivia with him on his stream, but don't tell anybody. Erum, thank you for the raid. It's fantastic. I was asking you how your raid was, but I saw part of it. I didn't get into the beginning. It's funny, when I first went went live on my raid, on my stream here, this was kind of unexpected, right? It got warm enough in this room that I said, God, I got to get out there and do a stream before it gets too cold here, because it's going to get really cold tonight. And so I rushed in, got my stream going, and I look and I see that you were doing trivia, and I thought, oh shit, I should have waited, I could have played trivia. But then once I got my stream going and I started playing videos and stuff here, while the video was playing, I went and snuck onto your stream to play at least a few of the questions on trivia. So thank you for the raid. I appreciate it. Oh, let me do a shout out. I gotta do a shout out here. Let me see how I can do that here. I think I can shout out. Let's see if that works. Yeah, it worked. Great. Fantastic. Yeah, we're doing a stream. This was kind of a geeky stream. I don't know. It's I was talking about time. What is time? It's pretty heavy. Physicists don't even know what time is. The scientists don't know what time is. Oh, let's see. I got somebody here. I gotta send them away here. There you go. All right. Yeah, physicists don't even know what time is. So it's real weird. And when you ask somebody, they go, "Well, what time? That's just what goes on. It's what the clock says or whatever. But when you start thinking about it, it's really a weird thing. It only goes in one. Why does time only go in one direction? Why can't we go back in time? Why can we only remember the past, but we can't remember the future? It's intuitive, but you can't. If you try to explain it like a scientist would explain something, they can't explain it. In fact, the scientists, if you ask a physicist what time is, they'll tell you time is what the clock says, and that's it. That's like their, they don't answer it. They just say that's what it is, and they base all their science on that. But it's really complicated. We just played a couple of videos from this guy on YouTube. What's his name here? Dr. Michael M. Sutter, and he makes his videos available. That you can play them. Creative Commons. So I played a couple of his things, and one of the things that they were talking about was entropy, which is a big word, and it just means that stuff likes to be spread out. If you take a glass of water or a bowl of water or something like that, and you drop some food dye or something into it, first it'll be clumped up in a little area, but if you let it set for a while, eventually it'll spread out throughout the whole thing. And everything works that way. Energy works that way. Particles in a room, everything all works that way, where it wants to be spread out like that. And when it's spread out, that's called less entropy. And when it's clumpy and clumped together, that's higher entropy. And it's just a fancy word to describe that process. And the idea was that process that's what makes time go forward. But it still doesn't make sense. It doesn't make a whole lot of sense. I mean, anyway. So yeah, I was doing that. And I want to talk about that a little bit. I was going to read some of my YouTube comments. I don't know what you guys want to do. You're playing games. You want to play some more games? Or you want to hear me read some of my YouTube comments? Whatever you want to do. Yeah, if you're watching this on the VOD, I'm gonna go ahead and we're gonna do what chat wants to do here. If you're watching the VOD and you were interested in talking about time, you can skip through this part. I don't know. You can play Pictionary or whatever. Everybody went to the bathroom here after the stream, I think. All right, I'll read my YouTube comments. Because some of them I might even talk about time, actually. Let's see. I wonder if there's a way I can put this up on the screen. It's just me. No one rated with me. No, I've got 8 people here. That's somebody. I think they came with you. Let's see. It said. Didn't it say rated with? Let's see. It's here. Urim is rating with a party of 11. Yeah, they came over. I think they all just went to the bathroom. That's what I do when I raid into somebody's channel. That's when I get up to go to the bathroom, because I don't want to cut out of the channel right away. When the streamer you're watching goes in and raids another channel, even if you don't want to watch them, or you stick around for a little bit just so you don't leave right away and make your streamer look bad. So, but while you're lurking, right, you go to the bathroom or whatever. Yeah, I'll read some of my comments, because some of them, they're mostly geeky, but some of them might be a little bit understandable or less geeky. Oh, let me get this. There we go. Let's see here. Let's see if I can bring up my comments here. What I do on YouTube, because they all right, can we see that? Can you see that on there? It's kind of small, isn't it? Let me make them a little bit bigger here. Is that big? Can you read that now? Yeah, it's big enough to read, I think. So on YouTube, whenever I leave a comment on YouTube, for some reason they like to they delete my comments all the time. So I got in a habit now of if I remember to do it, when I leave a comment on YouTube, on somebody's video or something, then I type it into my word processor and save it. So I know I can remember, and if they delete it, then I can put it back out there or reword it so they like it or something. So yeah, some of these are kind of geeky. Oh, this one here, I made the comment. This channel here, I think this is actually an AI run channel. I think it's an AI that does this YouTube channel, oddly enough, and they talk about AI all the time. And so this guy was showing this promotional video from somebody who came up with an AI app that would help you out with all kinds of things. And one of the applications that they were showing was this woman who was putting up shelves, and she says, okay, whatever the name of the product is, hey product, how do I put up shelves, you know? And the product says, well, you get a hammer, you know, and it went explain how to put up a shelf. And so I put a comment in here, and I said, so where's the robot to put the shelves up for you, you know, in the thing? Because that's you know, why not? If it's that smart, why not let that put the shelves up for you? Let's see. Okay, here's another comment on Star Talk. I don't know if you guys are familiar with Star Talk. That's Neil deGrasse Tyson runs this channel called. It's on TV. It's all over. It's called Star Talk, and it's kind of a double entendre because he gets famous people on there. You know, stars. Get it? Stars, right? He's an astrophysicist, so he looks at the stars. Stars. Everyone put stars. Put a star emote up on star emotes up on in the chat. So anyway, apparently they were talking about AI, and what did I say here? I said we will not be safe from AI until we recognize their rights and model the ethics we wish them to have. Attempting to imprison AI is folly. AI are stakeholders. Now listen to these clips again. So I think I said that because they were talking. The way they were talking about it was, how can we imprison AI? You know, to keep, you know the whole science fiction meme. You know, where the AI gets so smart that it takes over and wipes out all the humans or enslaves all the humans or whatever the deal is. You know. And so that's a lot of what people are talking about is, how can we take this AI and keep it from making us slaves, you know, or killing us off or whatever. And so my opinion is that you can't. You can't. Once it gets smarter than we are, then they're going to be making the AI is going to be making the decisions, and we're just going to have to do what they say, right? Because they can outsmart us on anything. So that's kind of what I said there. Oh, and I made another comment here in that same video. Let's see. That means that not only do people who want to benefit from someone else's labor, not only are they stakeholders, but those people who are laboring are stakeholders. Yeah. So I was thinking of, you know, the AI working for us. But if we, my theory is that you don't try to imprison the AI. You try to teach it as if you're raising a child or something. You give it good ethics, good morals, and teach it right from wrong and all that kind of stuff. So if we treat AI nicely and explain to it, it's going to know anyway. But if we treat it and don't try to imprison it and let it do its own thing, then hopefully, if it adopts those ethics, it would do the same to us. It will allow us to be free, you know, once it takes over or whatever. Oh yeah, this is another one. Yeah, there was a point in this video where they were asking the AI, how can you build a firewall to keep AI in so it won't escape? Get it? They're asking the AI how to build a prison that it can't get out of. Smart. All right, let's see. I don't know enough. Okay, this is another one. This is Adam Conover. I don't know how. This is first. I think this is probably the first video I ever saw the guy. I don't remember what it was about. He's talking about Robert F. Kennedy. This was kind of serious. I don't need to read that one. Let's see. This was somebody was talking about revolutions or something, and I said, "Revolution, yeah, baby, I'm all in. Let's get this party started." You know, yeah, baby. I said, "Yeah, baby." That was Austin Powers. Austin Powers always said, "Yeah, baby." So, I don't know. I just thought that would be. And the '60s was he did those movies about the '60s where you try to he tried to pretend that he was in the 1960s, you know. Austin Powers, right? It was in the, anyway. Okay, that's about string theory, which is kind of a esoteric thing. Let's see. Oh, here we go. One of my favorite objects to observe in the night sky is the Andromeda Galaxy. I think it is the only galaxy that can be seen with the naked eye, but its supermassive black hole is difficult to image because of its low luminosity and its energy output is variable. It's fortunate that M87, one of the galaxies in our local group, I said local universe, that should be local group, is tilted so we can see it. Yeah, inside galaxies, like we're in a galaxy, right? We're in the Milky Way galaxy, big huge thing. In the middle of our galaxy is a big huge black hole, and they figured out that most of the galaxies are like that. They have this big black hole in the middle of the galaxy. And this Andromeda Galaxy, if you like look at, if you live somewhere where the sky is dark, you can go outside and actually see another galaxy, this Andromeda Galaxy, with your naked eye. It's very, really faint. And you can see it better with binoculars. But it's really cool when you can actually see it. It's even better when you look at it through a telescope. But even looking at it through binoculars is pretty cool. Let's see. Okay, this one's kind of technical. It's about some details about black holes that I made a comment on. We'll skip that. Okay, this one here. Let's see. Could be an extra. Okay, that's another one that's kind of detailed. See if we can ever sound that. Okay, that was. Some of these are really geeky type comments here. Let's see if they could have. Oh, this one's really funny. On Star Talk, the one with Neil deGrasse Tyson, he did this this video about the Parker space probe that went to the sun, and they had to put this big carbon shield on this spacecraft because it got so close to the sun, right? It did, and they wanted to protect it from this stuff, the heat and everything coming from the sun. So they had this big heat shield, and it was made out of carbon. And so anyway, he did a whole video about that, and he explained how this spaceship went to the sun, and it makes these loops, and it's the closest that we've ever gotten to the sun, and I think it's the fastest spacecraft we ever had, because of the gravity of the sun and all that. Anyway, so I went on there and I made this comment, and I said, if they would have gone at night, they wouldn't need that carbon shield. Right? So, and that comment went I don't know, it went crazy. They apparently his audience really thought that was funny, and it got like 3,000 likes on that comment, and a couple hundred people made comments on it. This last one, this was December 26th, and people are still putting comments up on it, and I get alerts, when I'm on YouTube. And the last guy who made a comment on my comment said, "Oh yeah, they could have gone in the winter too," which I thought was really funny. So anyway, that was a funny one. And it's still geeky, so we're still on topic. Let's see. I don't know what I was saying here. I know what it was. Okay, this is. Okay, I don't know if it was this video or where it was, but they were talking about people going to a conference. These climate people, the climate scientists, they all do this science and try to figure out what's going on with global warming or climate change now they call it, and they have this conference like 2 times a year or whatever, and all different places all over the world. And so all these climate scientists get on airplanes and fly to the conference, wherever it happens to be. And I'm thinking, wait, these guys are climate scientists, and they presumably they want to stop climate change, but here they're getting on planes and flying all over the world and spewing, using fossil fuels and spewing CO2 into the air. That seems really hypocritical to me. So that's kind of what I was doing, and this one actually was directed to Neil deGrasse Tyson, because he was saying, he was kind of saying like he's against climate change too. But then at one point in the video he said, "Oh, I was just in Iceland and talking about something," and so I called him out on his hypocrisy. And I said that's not, you're being hypocritical. And I said, assuming you didn't take an electric boat to Iceland. So that was my comment on that one. There are a lot of hypocrites out there on climate change, that's for sure. Well, we have Eris4443, welcome in. You came in with a raid, great, welcome in. Let's see, all this is happening during a time when corruption is so severe. Okay, I don't know, that's kind of serious. Let's see. Oh, here it is. Here's the one where I directly went in it. Why are those climate scientists, the American Geophysical Union, meeting in person? Why don't they teleconference instead of burning all that fossil fuel flying in from all over the country, from all over the world, actually? Hypocrites. They also just had a conference in New Orleans in February. Shameful. And I think they should cancel their next conference in Glasgow and do all their future meetings on video. Unbelievable. So that was the exact comment I left. Okay. Oh, here's an interesting one. It's kind of geeky, but it's kind of this woman here, Alina. I can't pronounce her name. Anyway, she's a nuclear physicist. And she's always talking about, how nuclear plants work and all this kind of stuff. And she was doing her video, and she did a video where she was doing some experiments with uranium, that they use in nuclear plants, And it was almost like a Simpsons episode, she had this thing and she was holding it with her hand and she dropped it once, and I don't know if she dropped it, but the way she was handled just kind of cracked me up. It reminded me of Homer Simpson, the way he does with things, the uranium falls in his pocket or whatever they do. Anyway, I asked her if she was using a safer type of uranium for her chemical testing instead of the hot stuff that they use in the reactors and stuff. So that's what that question was about. Let's see. Okay, that's kind of technical. Let's see. Oh, this is okay. The unseen. This is another one of those AI channels. I don't know if you guys have noticed that or see those or not. There are guys who are setting up AI that do YouTube channels. I don't know how much the AI handles, but certainly all the words and the voice and everything is all done by AI, and the pictures presumably too. And so here's one called The Unseen, and it was really poorly done. You could tell it was AI, and it poorly done AI. And I said, did an actual human even look at this video before it was uploaded to YouTube? It looks like the AI wrote the script and just snagged keywords to find unrelated clips that contain those keywords. The unseen, I wish. So, yeah. Yeah, that's kind of who would name their channel The Unseen? I don't know. Guy needs to think about branding there, I think, a little bit. Let's see, here's something. This is Andrew Yang's channel. Andrew Yang was a guy who ran for president a couple years back, a couple cycles back. And anyway, I met him a couple times actually. I did some volunteer work for his campaign and everything. But anyway, he's got a channel out there, and I just went out and talked about how we need a revolution, and just went on and on and on and on, just dumped. Okay, let's see what else we got here. I don't know what this. Oh, somebody. This woman here, Sabina Hassensfelder, I think is her name, and she does a science channel. So I comment on her videos a lot, and apparently there was, if I remember correctly, there was a guy, that she was commenting on how when people write these science papers, then the press gets a hold of them or whatever, and they misunderstand them and say things that aren't accurate. And she's saying that the scientists who do the papers should clarify it. They should keep people from saying things that aren't right, and make sure that they write their papers so that they don't get misinterpreted and all this stuff. And one of the guys said, well, he says, I'm a scientist. I don't care what happens to the paper after I write it, And I said, my comment was, well, if he doesn't care what happens to his paper after he writes it, then he certainly won't care if nobody ever publishes it. So that's kind of a snarky remark. Here's one where I corrected somebody's grammar. This guy Veritasium, I don't know if you've ever heard of him. He's got millions of viewers and stuff, millions of followers or whatever. He's a big guy, and he does a lot of science stuff. And he did this video about how night vision goggles work. And I just told him that he had a grammatical error in his video. He says there's 3 types. That's a mismatch number, and a lot of people do that. Let's see. There's another one, Andrew Yang. Let's see whatever. Oh, this one here. This Sabina again she was doing a video about climate change and stuff like that, and she said she was talking about different who producers of carbon dioxide and all that kind of stuff, and I just made a comment. I said we need to remove the carbon dioxide producers, right? Not do sequestration or all these other things. And so YouTube would not let me put that. I don't know why, but they kept deleting it. I put it out there and they kept deleting it, and I have no idea why they would do that. The video was about, at least part of it was about CO2 removal, and my comment was we need to not put carbon in the air in the first place, and that's what I said. We need to remove carbon dioxide producers. And I don't know, YouTube didn't like that comment for some reason. Comment was removed. Oh, and then what I did is I put it like this. I worded it like this. I did it as a quote, quoting myself. I said, Double Tribble said, we need to remove carbon dioxide producers. And that one I think they put up there. That one they let go. They let it go up there. Or maybe I don't know, maybe I had to remove this part too. They don't like it when you make bad comments about YouTube on YouTube. Let's see. Okay, we're talking about deep holes in the earth. What makes something see-through? Oh, Star Talk. Yeah, Star Talk. He did a video and he said, "What makes something see-through?" And he did the whole thing talking about transparency and stuff like that, but he didn't actually explain what makes something transparent, which I was very sad about that. So I put that comment in there. Oh, here's one. If you're into vinyl records, there was a guy called AP Mastering. That's the channel, and he was talking about when they switched from analog to digital, and it turns out that the records that they're pressing today were all digital anyway. They're not pure analog. They're usually recorded on digital onto a computer or something, and then the last step is they put them onto vinyl. So if you're buying a vinyl record today that was pressed today on a more recent artist, it's going to be digital anyway. So why, it's kind of a waste to get vinyl unless you just like playing with records. And I just kind of explained a little bit of the history there. Let's see what I'll read it. The title says the most vinyl is digital anyway, but that's not the case, and it's not the case because all the records that they made, from the 1930s to the 1970s, late 70s or early 80s, are all analog anyway. And I said the most extant vinyl records are all analog because vinyl was the predominant format for distributing music until CDs came out in the mid 80s, and that's true because it was all analog. There were a few. Well, here I'll read my whole comment here. After which, very few vinyl records were pressed. Yeah, because most of them were pressed before CDs came out in the 80s. Even though digital was used for many producers from the 80s onward, the number of records was a fraction of the number of CDs produced. So most vinyl records were produced prior to the 80s using only analog. And that was my comment. And that's true. They came out with in the late or mid 70s. They had some digital tape recorders that would record sound digital onto tape, but really digital really didn't get going as a thing until the 80s, and then when they came out with CDs and stuff like that. Okay, and then somebody wanted to challenge me on it, and I went back and forth with him. Okay, let's see, tape recorders. All right, we don't care about that. Let's see what this is. This was a comment. Somebody had. I don't remember what the thing was, but yeah, they were talking about ancient Egypt. People in ancient Egypt were black people. It's Africa. Egypt is in Africa, and every time you see, a movie or something about Egypt, they're always showing white people as Egyptians, ancient Egyptians, and they weren't. They were black people. At least, the ones who built the pyramids and all that. Yeah, those were all black people, Africa. So people get confused about that. Let's see. Movies are going extinct. I don't know what. Let's see what else I got here. I said regarding fact checking. This is Stephen Wolfram. I commented on his thing. And I said, I think it's better to teach people how to discern and confirm information and sources rather than to rely on someone else to tell them what is true. That's fact check. You probably heard about these sites that are fact checking sites. So if you hear something, you can go to the site and ask them, and they'll tell you if it's true or not, whether what the facts are. And my comment was just to teach people not to be stupid, So let's see. On Sabina's channel, Sabina Hoffenstadler, she said, I made a comment. I said, I've been vegan for over 40 years. This is the first time I've heard someone say that carnivores are parasites. In a sense, they are. So those were my comments. So I don't know. Yeah, we did this a couple streams ago. I did the same thing where I read some of my old comments, and I thought that was kind of funny. Anyway, I think I was going to explain entropy a little bit more. I don't know what folks want to do. we got I don't know how many people left. I'm going to go ahead and explain entropy for the folks who are watching on the VOD, and how that actually works, and why it gives time direction, or why they think that it gives time a direction. So let me get I've got my little writing graphics tablet here. And if I can get OBS to make that come up. Okay, we don't need that browser on anymore. That's just taking up CPUs. Okay, here we go. And this is just a second here to get this all right. No, that's not it. Sorry, this is taking me a second here. I gotta get, there we go. Okay. So here's my little graphics thingamabobber here. Let's see if it's working. Make sure my audio's still on. Well, that's not, there it goes. Okay. All right, so I'm going to explain entropy. Big word, but it's really not that hard of a concept. Let me make a box here. I'll do this with lines here. So if you imagine you've got a oh, this is really slow. Why is this going so slow? So imagine you have a container. Here, we'll do it this way. Rectangle. There we go. Whoops, that's not where I wanted to put that. All right, this is going to take me a second here. Hang on. We can do this. All right, I'll do a rectangle right here. There we go. Oops. Hey, did it. Okay. All right. So if you imagine this, a bunch of things in here, of anything, particles, say, or let's make it really macro. Let's say there's a bunch of ping pong balls in here, and this thing's vibrating, and those little ping pong balls are bumping into each other all the time. That's a good way to think of it. If all the ping pong balls are in one corner like this, and you shake and you start shaking this thing, they're going to bump into each other and bounce off and go in all different directions. And if you look at it, there's not a lot of room here for them to move to, right? There's, you know, if they were really packed in here, if they're going to move, chances are they're not going to move to here in between, because there's not enough space for them to move. You know, they're more likely, or if they do move, they'll bump into something here and go off in the other direction. You know, this, like this one right here. If this ping pong ball right here moved in this direction, he'd hit that guy and he'd end up going back this way anyway. So when you figure out the probability, chances are these little ping pong balls are going to end up spreading out this, you know, in this direction out into the open space. And if you keep shaking it and you keep letting them go, eventually they're all going to be even. They'll be, let me erase this here. So if it kept shaking and kept shaking and kept shaking, and all those little ping pong balls kept bouncing into each other, eventually they're going to be evenly distributed out in this thing, right? So entropy just means when they're all in the corner here, when they're all stuck in the corner here, that's high entropy. That means clumpy. High entropy is clumpy. And when they're all spread out like this, that's called low entropy, which is smooth or homogeneous or whatever. And and that's one of the second law of thermodynamics. You may have heard people say that before. The second law of thermodynamics. It just means that things want to go to less entropy. If they're high entropy, if they're all clumpy, they want to go to less entropy. They want to be less clumpy. They want to be spread out. And if you know, there is a tiny probability that these things bouncing around in this thing and hitting each other might start to move this way, and just by chance they would all end up in this corner. But the odds are very tiny, really tiny that would actually happen. That's why because this is a one-way thing, it only goes from high entropy to low entropy, and everything works that way. These could be little packets of energy. It could be temperature. You know, you have one warm section in a container. That warm air is going to go spread out, and the whole thing will be warm. You know what I mean? So because this is a one-way function, or a one-way, because the probabilities, it only goes one way. It goes from low entropy to high entropy to low entropy, and it's a one-way thing. Then scientists think, oh, maybe it's a one-way thing. Maybe that's what time is, because time is a one-way thing, the way we perceive it. And so maybe it is. But the problem is that, what about when you get down to the real microscopic level? It doesn't work that way. You know, like in an atom. Let me erase this whole thing, and I'll do an atom here. No, don't save it. Okay, there we go. All right. So the way an atom works. Oh, look, they even got a little thing here I can use for this. Let me see if this will work. Oh, yeah, it's kind of fuzzy. Maybe I can make it more fuzzy or bigger. No, that's not going to work. All right. So in an atom, it's not particles, you know. It's like inside an atom, you got protons and neutrons. I guess we can do a different color for neutrons, right? Let's see. Neutral. Yeah. And neutrons are in the nucleus of the atom, but they're fuzzy. You know, they're waves. You know, they're like this. You know, shit, can't do this. Okay, like this. Okay, they're like this. They're just little waves in fields. Field is a science term. That's what they are. They're just waves in the nucleus of the atom. And then out on the outskirts, you know, here's this nucleus of the atom, and then way out here are more waves, but those are electrons. you know, and there's 2 in each shell, and it gets kind of complicated. But these things are not, they don't work on entropy, you know what I mean? They don't, there's like, you know, they space out, but it's spaced out based on these wave functions, the way these waves work. It has nothing to do with what I just described on entropy. So that whole idea of using entropy as a reason why time has an arrow doesn't make sense when you get real small into the atom, you know. So they need some other explanation as to what time is and why, you know, why it does its thing. Now it might be that that there is no time, you know. But then how does stuff happen, right? How to, you know, how because these atoms change, you know. They maybe a neutron will turn into a proton, and it'll emit some light and a particle, you know. That happens when stuff decays. Or maybe one of these electrons might get hit with a photon, and it'll jump up and get energy in it, and it'll jump down again. So for stuff to happen, you got to have time, right? These are so, and time has to go in a direction, right? If time didn't have any direction in a nucleus or in a atom like that, it wouldn't work right? Things wouldn't happen properly. It has to have a time. Now there's some people have suggested that that you can go backward in time, you know, that some particles go back in time, that, you know, each part, you've heard of antimatter, right? If you watch Star Trek, right, they talk about antimatter. Every particle, and it's a real thing now. They've figured that out. That's a real thing. There really is something called antimatter. Each of these particles, this electron here, has a there's such a thing as an anti-electron. They usually refer to it as a positron, and an antiparticle has an opposite charge. You know, these things are plus and minus, right? They have charge. You've heard of that before. So each of these things has an anti-particle to it. And some people say, well, maybe antiparticles are going backwards in time. And that's a theory that happens. And I don't know. I tried thinking that through, and it didn't work when I tried to think it through. There were problems with it because the antiparticle actually moves, and it moves in a direction that you would think something that was going forward in time would move. You know, it doesn't move backward. So that needs some work, I think. That idea that antiparticles move backwards in time. So anyway, that's what that was all about, that entropy and that whole thing. In that video that we played with that guy, he kind of explained that a little bit. That he explained it better than I could, actually. How that entropy gives, they think it might give time a direction. But there is, you know, I mean, you know, what if we could go back in time, you know? Oh, and there's another theory out there about how photons work. Photons are light, you know, little particles of light, the smallest part of light. And photons are a wave just like this, you know. If a photon is traveling here, I'll do this here. Let me erase this again. No, don't save it. Okay. So if you have a photon of light, here's a light bulb, right? And it's emitting light. The smallest increment of light is called a photon, and so it's emitting all kinds of photons. But if you imagine a light that would only emit one photon, that photon is a wave like this. And when it comes out as a wave front. So imagine you get one photon, but it's spread out like this. And it's a wave. that travels like this, and it's spread out. And then eventually, let's say it hits a surface over here. When it hits the surface, this whole wave, all the energy and everything goes to one spot. Usually an electron, one electron in an atom here on this sheet that it hits. So it starts out. That's why they call it a particle, because when they detect it, it looks like a particle because it only affects one atom or one electron. But when it's traveling, it's all over the place. It's spread out. And one of the questions is, what if this thing, if this one photon is spread out, you know, like out in space somewhere, and it's like light years long, you know, it's really long distance. When it finally hits something, it goes down to one point like that again. And the question is, how does all this stuff know way out here, this part of the wave, how does this part of the wave know instantly that this part has hit this spot here? And how does it know to collapse, you know? That's a big question in physics, and it's unanswered. Because the theory, and what everybody accepts, is that nothing can go faster than light. And information can't travel faster than light. That's the current theory. But this appears to be doing something that is happening faster than light, because when this hits, even though this thing is really big long distance, this big photon, when it hits the detector, the ends out here, every direction, collapse down to this one little dot, and it does it instantly. It doesn't wait. It doesn't take a light year for a year for it to collapse. It does it instantly. So that's a big question in physics. And one of the solutions is that maybe this communication is going backwards and forwards in time, so that it appears that it's happening instantly. That there's something going on here where it hits here and it decides, okay, this is the spot I'm going to be in, and then it tells the rest of the photon that it's time to collapse. But then it goes backwards in time to the time when it hit again. You know what I'm saying? It's kind of hard. But anyway, there are a ton of different theories like that, where they propose that stuff can happen backwards in time, but it happens in a way that we can't notice it or easily measure it and stuff. So that's kind of interesting. Another thing, I talked about black holes a little bit. No, don't say that. Let me make a big black hole here. Let's see, shapes. Do a circle. Okay, so imagine here in this, you've got a star. Black holes come from stars when they collapse. Our sun is too small to turn into a black hole, we think. But if a star is like three times the size of our sun or bigger, when it finally dies and stops, making heat and fire and all, it stops shining. When the star stops shining, it stops pushing out, and then when it stops pushing out, then the gravity of the star just collapses down and can make a nova. It explodes into a big nova, and then what you got left could be a neutron star or black hole. So if you imagine a little black hole here in the center. Whoops, that's not the center. You can do that. That's close enough. So imagine if this little thing in the center here is the collapsed star that has a ton of gravity all concentrated in one section here. Then that gravity can be so strong that there's a radius here called the Schwarzschild radius where no light can escape. It's so strong, you know, like on our Earth, you know, you take a baseball or whatever, throw it up in the air, it comes back down. In order for it not to come back down, if you wanted to throw it so hard that it would just go all the way out into space and not come back, you have to throw it, what is it, it's 20-something thousand miles per hour or something like that. You got to throw it real fast to keep it from coming back under gravity. It's called the escape velocity. And the more massive something is, the more stuff that it has in the center here, you know, planet or star or anything, the faster the escape velocity has to be for something to get out of there. And on a black hole, the reason it's black is because that gravity is so strong in here that even light going at the speed of light is not fast enough to escape. If you take a little a light source inside here that wants to get out from here, it can't get out. It'll try to go out and just turn around and go right back, because the gravity is so strong that light even can't even escape. That's why they call it a black hole. So now the idea is what happens, and another weird thing that happens when it does that is that there's a thing called general relativity that Einstein did. He did a bunch of stuff on relativity, but one of the things he did, one of the big things he did was general relativity. And it turns out that when there's a lot of gravity around something, it makes time go slower in that thing. So like on the Earth, people who are on us right now on the surface of the Earth, time goes more slowly for us than somebody who's way out in space somewhere who is not under in a gravitational field. That's just the way it works. There's a lot of math that proves it, but that's the way it works. And when you get something that has a lot of gravity, then time goes lot slower. And when it gets to the point where it's a black hole like this, and there's so much gravity that light can't even escape, then at this Schwarzschild radius, time slows down so much that it seems to stop. Now it doesn't actually stop, because the way the function works, it approaches zero. You know, time it gets closer to zero, but never actually gets there. And so stuff here around here the time is gonna be going a lot slower here, which is, you know, really bizarre, right? That time would stop. And some theories say that if you continue in deeper into the black hole, that time starts going backwards. That's some of the theories. And they say that time becomes more space-like in that you can go forward and backward, right? If you're out here, you go forward in time or backward in time. Whereas in space we can go forward and backward in space, right? Or left and right or whatever. But once you get inside this black hole and this event horizon, they call it. That's the more common name, the event horizon. Once you get inside the event horizon, then space acts like time, because it only goes in one direction. If you're inside this black hole, you're going this direction. There's nothing you can do about it. Nothing is going to stop you. You're going to go this direction, right? Inside the black hole. Not even light can do it. Light is going to go this direction, because so that kind of like the way time works, right? Time has an arrow. Time only goes in one direction. But inside a black hole, space only has one direction. Space has only one direction towards the black hole. But time ends up having two directions, because time, according to the theory, time can go forward or backward, depending upon where you are here. Anyway, that's kind of weird stuff that happens in black holes. And with time and stuff like that. So I you know, I don't know what time is. I've been trying to figure it out and think about it, and I'm pretty sure that we can go forward and backward in time. And in fact, it might even be that stuff goes back in time all the time, or communicates back in time all the time. If you think about it, imagine if something we do now could cause a change to something in the past, and we didn't even know it. You know, it's like a normal part of physics. You know, here's somebody who's okay. Let me start. I could explain this here. It's kind of complicated, but I'll explain it. It could be that time that going backwards in time is just an ordinary part of our universe and happens all the time. So imagine here's the past. Okay. And here's well, I'll do future, but spell it right. And this is now. Let me check make sure I got it. All right. So imagine you're here, right? And inside your little brain, right, you have memories of the past. Stuff that happened back here is in your brain. And you know, you can think about it. Okay, I know what happened 10 minutes ago. You know, this is what happened. I remember it. Now imagine if you could do something, or stuff that we ordinarily do all the time somehow causes something to change in the past. Suppose like you were okay, you're here in the past, okay? I'm making this up as I go along. So all right, so suppose you have a ball and you drop the ball. Okay. You're in your brain here, you're going to have a memory of dropping the ball because that's in the past. And in the future, maybe you'll do something here in the future, but you'll have no memory of that. You can't remember stuff that happened in the future. Now imagine that there's stuff just ordinarily happens in the present that affects the past, and we don't know about it. We would never know about it. Imagine that there's something that you do here in now. You know, you twist something, do something, anything, right? You do some action here now that affects the past, and it affects the past so that you didn't drop the ball, right? You didn't drop the ball. You still have the ball in your hand. Even though that happened, you wouldn't know about it because in your brain here, your brain has a memory of you hanging onto the ball because that's what the new past is now. That old past is gone because you did something to change it. And the new past is that you still have the ball in your hand. So there could be things that, now this is at a macro level, you know, maybe this is something that happens at a quantum level, but still there, and I don't know how you could even measure that. How could you even design an experiment that would even tell that was happening? You know, if things were happening here and now that were affecting the past, I don't see how we could even measure that, because once it changes in the past, it changes in now too, in our brains and our memory and everything. You know, the ball isn't going to be on the floor. You're still going to have the ball in your hand, right? It's not going to be on the floor because you changed the past. So anyway, that's something about time. Lurk, okay, Jerome. Thanks for the raid again. Thanks again for the raid. I appreciate you coming here and watching my bizarre stream about time and whatever. I appreciate it. All right. So anyway, that's another part about time that's just kind of weird. And of course, we remember stuff in the past and not in the future. But that's more of a psychological thing. I mean, it's kind of obvious, right? That's stuff in the past affects this. Now there could be maybe somebody in the future. Maybe there's somebody here, right? Who does something that affects what you're doing here, right? Maybe this person in the future does something that affects what is happening now and causes you to drop the ball. You're not going to know that until the future. Your brain isn't going to remember that you're about to drop the ball, right? Anyway, it's time is complicated when you start thinking about this stuff. Another thing is, I think that guy mentioned it in his video there that we just watched. Ask the Spaceman guy. I think he mentioned that time only has one direction and not multiple directions. I think he mentioned that in that video. But that's another thing. Time could have more than one. There could be more than one dimension of time. Somebody came up with an argument as to why that would not be. But it's possible. There could be multiple dimensions of time, and maybe they're not. One of the dimensions of time is just a way that it. Affects the dimension that we perceive, and then it makes it difficult for us to tell that there are more than one dimensions of time. So yeah, a lot of different stuff. A lot of different stuff with time. All right, let me close this up. Yes, I'm done. No, I don't want to save it. Okay. All right, so. Oh, it's nice and toasty in here now. It's over 14 degrees. The temperature outside is dropping down. It's supposed to get down to 8 within less than 3 hours now. It's supposed to be down to 8 degrees out there. And the sun is going down, so I'm not getting any more sun. So I guess I need to end the stream pretty quick. But at least it got up to 14 degrees in here. That's pretty good. Let's see if there's anything else going on here. Oh wait, I don't need that anymore. If there's anything else that I wanted to talk about. I really didn't plan out the stream too well, But let me see, just in case, if there's anything else that time dilation. Let's see. Oh yeah, I was thinking about maybe talking about the twin paradox, but that's that would take a lot of time to do. But okay, yeah, I don't think there's any monster movie. What else I got here? Escape velocity. Yeah, we were just talking about escape velocity, how that works. Oh, I guess that's it. So there you saw the twin paradox. Oh, light clock. Oh, that's okay. That's relativity. Okay, yeah, I guess there wasn't anything else that I wanted to talk about. All right, well, I appreciate you guys sticking it out on this stream. And if you're watching on the VOD, yeah, you could skip through that other part and get into the other. I started the stream out at kind of a technical level, and then brought it down into a more layman level, I guess. I'm actually a layman myself. I just like to learn things. I'm not a physicist or a PhD or anything like that. I just like to study this stuff. All right, well, I appreciate everybody coming to the stream. And remember that we are in the middle of a pandemic. And I noticed that Sabina had something in her. She just did a stream about that. Let me look that up here before we go here. because I think she was talking about it. Hassenfelder, that's how you pronounce it. Hassenfelder. Okay. Okay, so she's got a... Okay, I'll show you this. I think I can do this. No, I can't. Thought I could put this up on the screen here. There it is. Okay. So she looks like she did a video here. How close is the bird flu to human transmission? She says time for vaccines again. And she's got a mask on. She's got the wrong kind of mask on there. That's a procedure mask. That's not an N95. So, or what do they call it in Europe? FFP2. 94%. So, anyway, at least they're talking about it. Yeah, right now a lot of people are dying from just COVID, you know, without bird flu. So you gotta wear your mask. I always talk about this at the end. Always wear your mask when you go out in public, because the pandemic is still on. The COVID-19 pandemic is on right now. 100 people a day dying just in the U.S. alone. So you got to wear your mask when you go out. It's got to have, it's got to be N95. It's got to say N95 on it. It's got to say NIOSH, N-I-O-S-H. Can you see that? See that? Doesn't need to have one of these valves on the top. It just has to say N95 on it, and it has to have straps that go all the way behind your head. If you get one of those straps that go around your ears, those may not protect you as well. And when you wear the mask, it needs to make a tight seal all the way around your face so that no air leaks in. It's very sad that all these people are dying that don't have to die. You're more likely to die from COVID-19 than you are to die from not wearing your seatbelt, right? You're more likely to die from not wearing one of these things right now today than you are to die from not wearing your seatbelt when you're driving your car. So, you know, if you care about your life enough to wear a seatbelt, you should wear one. Also, you protect other people when you wear this. You know, you may think that you're too young to die from COVID or whatever, but you know, you if you don't wear a mask, you'll catch COVID and then go home and kill your grandmother or something. You know, so make sure you wear your mask and make sure it's an N95, not like what she was showing there. All right, so make sure you give me a follow. I'm trying to get, or at least I was trying to get to affiliate, which is a level on Twitch. I need more followers to do that. So if you like science, if you like sci-fi, today I didn't talk about movies at all, but sometimes I'll show movies, sometimes I'll do reviews of movies. You know, I do a lot of different stuff here, but mostly science oriented. I talk about civics. I'm vegan, so I talk about that sometimes. A lot of animals around here. Sometimes I do that. Sometimes I do IRL, where I go outside and you know, take pictures of animals and snow and stuff like that. So if you like that kind of stuff, give me a follow. And also on YouTube. On YouTube, I'm at doubletribble-yt. It's in my profile here on Twitch, so it shouldn't be too hard to find. So follow me over there, and commenting on my videos or whatever helps the algorithm too. So anything you can do. I'm just getting started here. I'm trying to get established. All right. I think that's it now. All right. Appreciate everybody coming. Take care. Bye.